Somewhere deep in the cosmos, beyond the stars we can see, lies a hidden force so powerful it's pulling entire galaxies. Not just one or two, but countless star systems, whole clusters, all being drawn in the same mysterious direction. Even our own Milky Way, with its billions of stars, is caught in this invisible grip, racing silently through space toward an unknown destination. Astronomers first noticed it when galaxies refused to behave the way the universe's expansion predicted. They weren't just drifting apart as expected. They were moving off course, as if something massive, something unseen, was reeling them in. What could possibly exert such influence across hundreds of millions of light years? Is it a hidden concentration of galaxies too distant to see? A vast reservoir of dark matter bending space and time itself? Or something stranger? A structure beyond our comprehension, shaping the destiny of the cosmos? For decades, this mystery has remained shrouded behind veils of dust and stars in our own galaxy, a region so obscured that astronomers call it the zone of avoidance. And yet the pull is undeniable. Whatever it is, wherever it hides, its presence is written into the very motions of the universe. Like and subscribe as we journey into one of the most baffling enigmas in modern astronomy. This is the story of the Great Attractor. The year was 1973. Bell-bottom jeans were in fashion, Pink Floyd had just released The Dark Side of the Moon, and a young astronomer named Vera Rubin was about to stumble upon something that would shake the foundations of cosmology. Rubin wasn't looking for cosmic monsters or galactic highways. She was simply trying to understand how spiral galaxies rotate. What Rubin found changed everything. She discovered that the outer edges of spiral galaxies were spinning way too fast. According to everything we knew about physics, these outer stars should have been flung into space like mud flying off a spinning bicycle wheel. The visible matter in these galaxies simply didn't have enough gravitational pull to hold the outer stars in their orbits. But the stars weren't flying away. Something invisible was holding them in place. This was humanity's first concrete evidence of dark matter, a mysterious substance that makes up about 85% of all matter in the universe but doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes, yet it outweighs all the stars, planets, and gas clouds in the universe by more than 5 to 1. Rubin's discovery was revolutionary, but it also opened Pandora's box. If we couldn't see most of the matter in individual galaxies, what else were we missing on larger scales? Were there invisible structures lurking throughout the cosmos, shaping the universe in ways we couldn't even imagine? The answer to that question would come from an entirely different line of research. While Rubin was studying galaxy rotation, other astronomers were engaged in what seemed like a completely separate project. Mapping the expansion of the universe by measuring how fast distant galaxies were moving away from us. Ever since Edwin Hubble's groundbreaking observations in the 1920s, astronomers had known that the universe was expanding. Distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This relationship, known as Hubble's law, suggested that the universe had begun in a cosmic explosion, what we now call the Big Bang. But by the 1970s, astronomers had sophisticated enough instruments to measure galaxy velocities with unprecedented precision. They expected to find a clean, simple pattern. Galaxies moving away from us at speeds directly proportional to their distance, like raisins in rising bread dough spreading apart as the dough expands. What they found instead was far more complex and intriguing. Yes, distant galaxies were moving away from us due to cosmic expansion. But they were also moving in specific directions that couldn't be explained by expansion alone. It was as if the raisins in the bread weren't just spreading apart uniformly, but were also all sliding toward one corner of the loaf while the dough expanded. These unexpected motions were called peculiar velocities, not because they were strange, though they certainly were, but because peculiar is the technical term astronomers use for motion that deviates from the overall expansion of the universe. And the peculiar velocities that astronomers were measuring were huge, hundreds of kilometers per second in specific directions. The first major clue came from studying our own cosmic backyard. Our Milky Way galaxy is part of what astronomers call the local group, a small cluster of galaxies that includes our nearest major neighbor, the Andromeda Galaxy, along with about 80 smaller galaxies scattered across a region about 10 million light-years in diameter. When astronomers carefully measured the motion of our entire local group through space, they made a startling discovery. We weren't just participating in the general expansion of the universe. We were also racing through space at 627 kilometers per second in the direction of the constellation Hydra. To put that speed in perspective, that's over 2.2 million kilometers per hour, fast enough to travel from Earth to the Moon in less than 3 hours. If you could somehow travel at this speed, you could circle the Earth's equator in just 18 seconds. Yet this incredible velocity represents the motion of our entire local group of galaxies, carrying billions of stars and potentially millions of civilizations on a cosmic journey toward something unknown. But the mystery deepened when astronomers looked beyond our local group. Survey after survey revealed that hundreds of other galaxy groups and clusters were all moving in roughly the same direction as us. It was like discovering that not just your family car, but every vehicle within a 1,000-mile radius was somehow drifting toward the same invisible destination. Something was pulling on the galaxies. Something massive beyond imagination was exerting its gravitational influence across hundreds of millions of light-years, causing a coordinated migration of cosmic proportions. But what could possibly be that powerful? The hunt for this cosmic puppet master began in earnest in the early 1980s, led by a group of 7 astronomers who would become legendary in the field of cosmology. Alan Dressler of the Carnegie Observatories assembled a team that included Sandra Faber, David Burstein, Roger Davies, Donald Lindenbell, Roberto Turlovich, and Gary Wegner. The astronomical community would later dub them the Seven Samurai, a reference to the famous 1954 Japanese film about 7 warriors who band together to fight overwhelming odds. The 7 samurai faced their own overwhelming odds. They were trying to map the 3-dimensional structure of the universe using techniques that were still in their infancy. Unlike measuring the distances to nearby stars, determining how far away a galaxy is requires sophisticated analysis of its intrinsic brightness and other properties. For spiral galaxies, they used something called the Tully-Fisher relation, which connects a galaxy's rotation speed to its total luminosity. Faster rotating galaxies are more massive and therefore brighter, allowing astronomers to estimate distance by comparing a galaxy's observed brightness to its expected brightness. For elliptical galaxies, they used the fundamental plane, a relationship between size, surface brightness, and internal stellar velocities that serves a similar purpose. These techniques required painstaking observations with some of the world's largest telescopes. Each galaxy had to be studied individually, its spectrum analyzed to measure both its recession velocity due to cosmic expansion and its peculiar velocity due to gravitational influences. The work was tedious, time-consuming, and fraught with potential sources of error. But the 7 samurai persevered, and by 1986 they had assembled a dataset unlike anything that had ever existed before. Precise distance and velocity measurements for hundreds of elliptical galaxies spread across a significant fraction of the sky. When they plotted their results, a clear and startling pattern emerged. Galaxy after galaxy, cluster after cluster, all showed evidence of motion toward the same region of space. The effect was strongest for nearby galaxies and gradually diminished with distance, exactly as you'd expect if some massive object was gravitationally attracting everything within a certain radius. The Seven Samurai calculated that everything within about 250 million light-years of Earth was participating in this cosmic migration. To put that distance in perspective, light from the edge of this region began its journey to Earth when the first dinosaurs were emerging on our planet. We're talking about a volume of space containing tens of thousands of galaxies, all streaming toward the same destination. That destination lay in the direction of the constellations Hydra and Centaurus, in a region of sky that was largely hidden from optical telescopes by the thick disk of our own Milky Way galaxy. The Seven Samurai realized they had discovered evidence of the most massive gravitational anomaly in the known universe, lurking behind a cosmic curtain that prevented direct observation. In their landmark 1986 paper, published in the Astrophysical Journal, the Seven Samurai gave this mysterious cosmic magnet a name that would capture imaginations around the world: the Great Attractor. The name was perfect. It was both scientifically descriptive and evocatively mysterious. The Great Attractor, it sounded like something from science fiction, yet it was based on rigorous observational evidence. Here was proof that our universe contained structures so massive and influential that they could orchestrate the motions of galaxies across distances that defied human comprehension. But naming the Great Attractor was just the beginning of the mystery. The real challenge was figuring out what this cosmic leviathan actually was. The first step was trying to estimate its mass. Using Newton's laws of gravity and the observed velocities of galaxies streaming toward it, the Seven Samurai calculated that the Great Attractor had to contain the equivalent mass of tens of thousands of galaxies like our own Milky Way. Let's pause for a moment to contemplate what that means. Our Milky Way galaxy contains roughly 400 billion stars, with a total mass equivalent to about 1 trillion suns. The Great Attractor appeared to have the mass of tens of thousands of such galaxies. That's a mass equivalent to roughly 10 quadrillion stars, a number so large that if you wrote it out in full, it would be a 10 followed by 15 zeros. To put this in more tangible terms, imagine that every star in the Great Attractor region was replaced by a grain of sand. You would have enough sand to cover the entire continental United States to a depth of several meters. And remember, we're talking about stars here, objects so massive that our Sun, which contains 99.8% of all the mass in our solar system, would be just an average member of this cosmic collection. But here's where the mystery deepened into something truly puzzling. When the Seven Samurai and other astronomers pointed their telescopes toward the Great Attractor region, they didn't see nearly enough galaxies to account for all that mass. It was like calculating that a building should weigh 1,000,000 tons based on how much the ground sags beneath it, then discovering that when you actually look at the building, it appears to weigh only 1,000 tons. Where was all the missing mass? This discrepancy led astronomers to consider several mind-bending possibilities, each more intriguing than the last. The first possibility was that there were thousands of galaxies hiding behind the dust and gas of our own Milky Way's disk. Our galaxy is shaped like a flattened disk, with a thick concentration of stars, gas, and dust in the galactic plane. This material creates what astronomers call the zone of avoidance, a band across the sky where distant objects are hidden from view by the intervening material in our own galaxy. It's like trying to see what's on the other side of a house while standing inside it. The walls block your view. In this case, the walls are made of cosmic dust particles that absorb and scatter light from distant galaxies, making them invisible to optical telescopes. The zone of avoidance covers about 20% of the sky, and by pure bad luck, the Great Attractor appeared to be located right in the thick of it. Perhaps this cosmic coincidence explained the mystery. Maybe there were thousands of massive galaxies hiding behind our galactic disk, invisible to our telescopes but detectable through their gravitational effects. The second possibility was even more exotic. Perhaps the Great Attractor was primarily composed of dark matter, the same invisible substance that Vera Rubin had discovered in individual galaxies. Maybe there was an enormous concentration of dark matter in that region of space, with relatively few visible galaxies embedded within it like raisins in an invisible cake. This idea was both thrilling and terrifying. If true, it would mean that the universe contained massive structures made almost entirely of invisible material, cosmic icebergs where only the tiny visible tip could be detected by our telescopes, while the vast bulk remained hidden beneath the surface of observability. The third possibility was perhaps the most intriguing of all. Maybe the Great Attractor represented something entirely new, a type of cosmic structure that challenged our fundamental understanding of how the universe works. Perhaps it was a primordial black hole left over from the Big Bang, or a concentration of some exotic form of matter that we had never encountered before. Each possibility had profound implications for our understanding of the cosmos, and astronomers were determined to figure out which one was correct. The investigation of the Great Attractor would require some of the most ingenious astronomical detective work ever attempted. If you can't see your target directly, you have to find other ways to study it. Fortunately, the electromagnetic spectrum extends far beyond the narrow range of wavelengths that our eyes can detect, and different types of light interact with cosmic dust in different ways. The key insight was that longer wavelengths of light can penetrate cosmic dust more effectively than shorter wavelengths. It's the same principle that allows fog lights on cars to use yellow or red light to improve visibility in foggy conditions. Longer wavelengths aren't scattered as much by small particles. Astronomers realized that if they could observe the Great Attractor region in infrared light, which has longer wavelengths than visible light, they might be able to peer through the zone of avoidance and see what was hidden behind it. The first major breakthrough came in the 1990s with the development of sensitive infrared detectors and space-based infrared telescopes. The infrared astronomical satellite IRAS, launched in 1983, had provided tantalizing glimpses of infrared sources in the Great Attractor region, but it lacked the resolution and sensitivity needed for detailed studies. More powerful infrared surveys followed, including ground-based projects that took advantage of the fact that Earth's atmosphere is partially transparent to certain infrared wavelengths. Astronomers developed new techniques for removing the effects of atmospheric water vapor and other interfering factors, allowing them to create increasingly detailed infrared maps of the hidden cosmos. What they found was both reassuring and puzzling. The infrared surveys did indeed reveal numerous previously unknown galaxies in the zone of avoidance. Many of these galaxies were massive, some even larger than our own Milky Way, and had been completely invisible to optical telescopes. One of the most significant discoveries was the Norma Cluster, a massive collection of galaxies located right in the heart of the Great Attractor region. The Norma Cluster contains hundreds of individual galaxies and has a total mass equivalent to about 1,000 Milky Way galaxies. It had been lurking there all along, completely hidden from optical view but blazing brightly in infrared light. But even as astronomers cataloged discovery after discovery in the infrared, they realized that they still hadn't solved the Great Attractor mystery. The newly discovered galaxies and clusters, impressive as they were, still didn't add up to enough mass to explain the Great Attractor's gravitational effects. They had found some of the missing pieces of the puzzle, but many more remained hidden. This is where radio astronomy entered the picture, providing astronomers with an even more powerful tool for piercing the cosmic veil. Radio waves have much longer wavelengths than infrared light, making them virtually unstoppable by cosmic dust. But radio astronomy offered something even more valuable than just another way to see through the zone of avoidance. It provided a method for detecting and measuring the distances to galaxies based on their hydrogen content. Hydrogen is the most common element in the universe, making up about 75% of all ordinary matter. Most of this hydrogen exists in what astronomers call the neutral state, hydrogen atoms with their single electron still attached. These neutral hydrogen atoms have a remarkable property. They emit radio waves at a very specific frequency of 1420.4 MHz. This emission line, known as the 21 centimeter line, named for the wavelength of the radio waves, acts like a cosmic fingerprint. Every galaxy contains vast amounts of neutral hydrogen gas, the raw material from which new stars are formed, and this hydrogen broadcasts its presence throughout the universe at the 21 centimeter frequency. For astronomers studying the Great Attractor, the 21 centimeter line was like a gift from the physics gods. Not only could radio telescopes detect galaxies that were completely invisible at other wavelengths, but they could also measure the galaxy's distances and velocities with remarkable precision. Here's how it works. When a galaxy is moving away from us due to cosmic expansion, the radio waves from its hydrogen gas are stretched to slightly longer wavelengths, a phenomenon known as redshift. The amount of redshift tells astronomers how fast the galaxy is receding, which in turn reveals its distance through Hubble's law. But the 21 centimeter line also reveals peculiar velocities, the additional motion that galaxies have on top of their recession due to cosmic expansion. If a galaxy is being gravitationally attracted towards something like the Great Attractor, its radio waves will show a combination of redshift due to cosmic expansion and either additional redshift or blue shift due to its peculiar motion. By the 1990s, radio astronomers had launched systematic surveys of the zone of avoidance using this technique. Projects like the Parkes HI Zone of Avoidance Survey used large radio telescopes to scan the hidden regions of the sky, mapping the distribution and motions of hydrogen-rich galaxies that had never been seen before. The results were revolutionary. Survey after survey revealed thousands of previously unknown galaxies hiding behind the zone of avoidance. These weren't just small, insignificant galaxies. Many were massive spiral systems comparable to or even larger than our own Milky Way. The radio surveys also revealed something even more important: the large-scale structure of the cosmic web in the Great Attractor region. Rather than finding a single monolithic concentration of mass, the surveys showed that the Great Attractor was actually a complex, multi-component structure embedded in a vast network of galaxy filaments and clusters. Imagine looking at a major highway interchange from a great distance. At first, it might appear to be a single structure, a knot of roads and ramps all tangled together. But as you get closer and can see more detail, you realize that it's actually composed of multiple highways, on-ramps, off-ramps, overpasses, and connecting roads, all working together as an integrated transportation system. That's what the radio surveys revealed about the Great Attractor. It wasn't a single massive object, but rather a complex intersection in the cosmic web, a region where multiple filaments of galaxies converged and interacted. But radio astronomy was just one tool in the growing arsenal that astronomers were using to study the Great Attractor. X-ray astronomy provided yet another crucial piece of the puzzle. Galaxy clusters are filled with extremely hot gas, millions of degrees hot, that emits copious amounts of X-rays. This hot gas, which astronomers call the intracluster medium, can outweigh all the stars in a cluster's galaxies combined. By mapping the X-ray emission from galaxy clusters, astronomers can determine not only the total mass of the cluster, including its dark matter content, but also study the cluster's internal dynamics and evolution. X-ray telescopes like the Chandra X-ray Observatory and the European Space Agency's XMM Newton have mapped the hot gas in dozens of galaxy clusters in the Great Attractor region. These observations have revealed that the region contains multiple massive clusters, each filled with hot gas and embedded in even more massive halos of dark matter. One of the most important results from X-ray astronomy has been the confirmation that the Great Attractor region really does contain enough total mass, including dark matter, to explain its gravitational effects on surrounding galaxies. The mystery of the missing mass has been solved. It wasn't missing, it was just invisible. The X-ray observations also revealed something unexpected about the structure of the Great Attractor region. Rather than being dominated by a single, central massive object, the region appears to be a complex system of multiple galaxy clusters and dark matter halos, all interacting gravitationally with each other. This discovery has profound implications for our understanding of cosmic structure formation. It suggests that the Great Attractor didn't form as a single, isolated object, but rather as part of the hierarchical process by which structure grows in the universe, smaller objects merging to form larger ones, which in turn merge to form even larger structures. While astronomers were using radio and X-ray observations to map the Great Attractor's components, another group of researchers was taking a completely different approach to the problem. Instead of trying to observe the Great Attractor directly, they were using supercomputers to simulate the formation and evolution of cosmic structure, testing whether their theoretical understanding of the universe could predict the existence and properties of something like the Great Attractor. These cosmological simulations start with the initial conditions of the universe as observed in the cosmic microwave background, the afterglow of the Big Bang. The simulations then evolve these initial conditions forward in time using the known laws of physics, particularly Einstein's theory of general relativity and our understanding of dark matter. The most sophisticated of these simulations, such as the Millennium simulation and its successors, follow the evolution of billions of dark matter particles over more than 13 billion years of cosmic history. They show how tiny initial density fluctuations, amplified by gravitational instability, eventually grow into the cosmic web of filaments and nodes that we observe today. Remarkably, when these simulations are run for volumes of space comparable to our local universe, they consistently predict the formation of massive structures in exactly the locations where we observe them. The simulations predict that there should be something like the Great Attractor in the direction of Hydra and Centaurus, at approximately the right distance and with approximately the right mass. This agreement between theory and observation is one of the great triumphs of modern cosmology. It gives us confidence that we really do understand the basic physics governing the formation of cosmic structure, even when we can't see all the components directly. The simulations also make predictions about the internal structure of regions like the Great Attractor. They suggest that these massive attractors should be composed of multiple galaxy clusters and dark matter halos, connected by filaments of lower density material, exactly what the observational surveys have found. Perhaps most importantly, the simulations show that the Great Attractor is not unique. Similar massive structures should exist throughout the universe, serving as nodes in the cosmic web where galaxy flows converge. The Great Attractor was important not because it was the only structure of its kind, but because it was the first one that astronomers discovered and studied in detail. As observational techniques improved and surveys covered larger volumes of space, astronomers began to discover that the Great Attractor was indeed part of an even larger cosmic structure. The plot, as they say, was about to thicken dramatically. The breakthrough came in the late 1990s and early 2000s, as increasingly sophisticated peculiar velocity surveys mapped galaxy motions over much larger volumes than the Seven Samurai had been able to study. These surveys used improved distance measurement techniques and more powerful telescopes to observe thousands of galaxies across significant fractions of the observable universe. What they found was both expected and shocking. Expected, because the surveys confirmed the existence of the Great Attractor and refined measurements of its mass and structure. Shocking, because they revealed that our motion toward the Great Attractor was itself just part of a much larger flow pattern. Imagine following what you think is a small stream, only to discover that it feeds into a river, which itself flows into an even larger river, which eventually reaches the ocean. That's analogous to what happened with our understanding of cosmic flows. The new surveys showed that everything within about 700 million light-years of Earth, including the Great Attractor itself, was streaming toward an even more distant and massive structure. This ultimate destination was the Shapley supercluster, also known as the Shapley concentration, located about 650 million light-years away in the constellation Centaurus. The Shapley supercluster makes the Great Attractor look small by comparison. It contains the mass equivalent of about 10,000 Milky Way galaxies distributed across more than 30 individual galaxy clusters. If the Great Attractor is like a major city attracting surrounding towns, the Shapley supercluster is like a megacity attracting everything within a 1,000-mile radius. Named after the pioneering astronomer Harlow Shapley, who first cataloged many of the galaxies in this region, though he had no idea of their collective significance, the Shapley supercluster represents one of the most massive concentrations of matter known in the observable universe. But the story doesn't end there. As surveys became even more comprehensive, covering larger volumes and measuring more galaxy velocities, astronomers began to piece together a picture of cosmic flows on the largest observable scales. In 2008, a team led by Alexander Kashlinsky at NASA's Goddard Space Flight Center announced a discovery that sent shockwaves through the astronomical community. Using data from the Wilkinson Microwave Anisotropy Probe, WMAP, which had mapped the cosmic microwave background in unprecedented detail, Kashlinsky's team claimed to have detected evidence of what they called the dark flow. The dark flow was supposed to be a bulk motion of galaxy clusters on scales so large that it challenged our understanding of cosmology itself. According to Kashlinsky's analysis, everything within billions of light-years was streaming in the same direction at about 600 kilometers per second toward a region of space far beyond what should be gravitationally influencing our local cosmic neighborhood. The implications were staggering. If real, the dark flow suggested that our observable universe was being influenced by structures or forces beyond what we can see, perhaps matter that existed beyond our cosmic horizon, or even evidence of other universes in a cosmic multiverse. The dark flow announcement triggered intense debate and follow-up studies. Some astronomers argued that the signal was real and represented a fundamental new discovery about the large-scale structure of the universe. Others contended that it was a systematic error in the data analysis or a statistical fluke. Subsequent observations with more sensitive instruments, particularly the European Space Agency's Planck satellite, failed to confirm the dark flow signal. Most astronomers now believe that the original detection was indeed a systematic error, though the debate continues in some circles. Whether or not the dark flow is real, its proposed discovery highlighted a fundamental truth about our universe. We are embedded in a cosmic web of structure and motion that extends far beyond what we can directly observe. The Great Attractor, massive as it is, represents just one node in this vast network. This brings us to one of the most fundamental observations in all of cosmology: the cosmic microwave background dipole. When astronomers map the temperature of the cosmic microwave background across the entire sky, they find that it's not perfectly uniform. Instead, it shows a subtle pattern. The radiation is about 0.0033 Kelvin warmer in one direction and correspondingly cooler in the opposite direction. This temperature variation, known as the dipole, is caused by our motion through the universe. It's the cosmic equivalent of the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched when it's approaching you and lower-pitched when it's moving away. The dipole tells us that our local group of galaxies is moving at 627 kilometers per second toward a point in the sky in the direction of the constellation Leo. This motion is the sum of all the gravitational influences acting on us, the pull of the Great Attractor, the Shapley supercluster, and all the other massive structures in our cosmic neighborhood. Remarkably, the direction indicated by the cosmic microwave background dipole aligns almost perfectly with the direction toward the Great Attractor and the Shapley supercluster. It's as if we have multiple cosmic GPS systems all pointing in the same direction, confirming that we really are being pulled through space by these massive gravitational attractors. Modern surveys have been able to account for about 50% of our dipole motion based on the gravitational effects of known structures like the Great Attractor and Shapley supercluster. The remaining 50% presumably comes from even more distant structures that we haven't yet identified or fully characterized. This partial accounting represents both a success and a challenge for cosmology. It's a success because it shows that our understanding of cosmic structure and gravitational dynamics is basically correct. We can predict a substantial fraction of our cosmic motion based on the distribution of matter that we observe. It's a challenge because it reminds us that there are still massive structures out there that we don't fully understand. Some of these mysterious influences have names and approximate locations. There's the Perseus-Pisces supercluster, located about 250 million light-years away in a different direction from the Great Attractor. There's the massive Coma supercluster and the Hercules supercluster. Each of these structures contributes to the cosmic gravitational field that determines our motion through space. But there are also hints of even more distant structures that may play a role. Surveys have detected what appear to be massive filaments and superclusters at distances of more than 1 billion light-years, far enough away that their light began its journey to us when the Earth was still a young planet and life was just beginning to evolve. The discovery of these distant structures has revealed that the universe has a hierarchy of organization that extends across the largest observable scales. Galaxies are organized into groups and clusters. Clusters are organized into superclusters. Superclusters are connected by filaments that span hundreds of millions of light-years. And the entire network forms what astronomers call the cosmic web, a three-dimensional pattern of matter and energy that encompasses the entire observable universe. The Great Attractor sits at a major intersection in this cosmic web, a place where multiple filaments converge and create a gravitational focus that influences galaxy motions across vast distances. Understanding its role in the cosmic web has been crucial for placing our own galaxy's motion in its proper context. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii announced a discovery that fundamentally redefined our understanding of our place in the universe. Using advanced techniques for measuring galaxy distances and velocities, Tully's team had mapped the flow patterns of galaxies in our cosmic neighborhood in unprecedented detail. What they found was remarkable. Our local supercluster, which includes the Milky Way, the Virgo cluster, and dozens of other galaxy groups and clusters, was not a gravitationally bound structure as previously thought. Instead, it was just a small part of an even larger system of galaxy flows. Tully and his colleagues identified this larger structure as a supercluster of superclusters, a vast region of space within which all galaxy motions are gravitationally coordinated. They named it Laniakea, which means immense heaven in Hawaiian. Laniakea spans about 500 million light-years and contains the mass equivalent of about 100 trillion suns. To put that in perspective, if our solar system was shrunk down to the size of a grain of sand, Laniakea would be about the size of North America. The boundaries of Laniakea are defined not by visible structures, but by the watershed of galaxy flows within it, regions where the gravitational influence of Laniakea's mass concentration dominates over that of neighboring superclusters. It's analogous to how a river basin is defined by the region where all water flows toward the same river system. And at the heart of Laniakea's gravitational field, the Great Attractor. This discovery placed the Great Attractor in its proper cosmic context. It's not just a random concentration of mass that happens to be pulling on nearby galaxies. It's the central hub of one of the largest gravitationally coordinated structures in the known universe, the focal point toward which 500 million light-years worth of galaxies are flowing. The Laniakea discovery also revealed something profound about the nature of cosmic structure. Unlike galaxy clusters, which are held together by their own gravity and will persist indefinitely, superclusters like Laniakea are temporary features. They exist only because the universe is still young enough that gravity can overcome cosmic expansion on these scales. In the future, as the universe continues to expand and the mysterious dark energy that drives this expansion becomes more dominant, the galaxy flows that currently define Laniakea will reverse. The various clusters and superclusters will begin moving away from each other, and Laniakea will dissolve into isolated island universes. Computer simulations suggest that this process will begin in earnest in about 100 billion years, a time span so vast that it's difficult to comprehend. For comparison, 100 billion years ago, the universe was less than 4 billion years old, and the first galaxies were just beginning to form. 100 billion years from now, most stars will have exhausted their fuel, and the universe will be a much darker, colder place than it is today. But for now, during this brief cosmic moment when gravity still dominates over expansion on the largest scales, the Great Attractor reigns as one of the most influential structures in our corner of the universe, orchestrating the motions of countless galaxies across unimaginable distances. The modern picture of the Great Attractor that has emerged from decades of multi-wavelength observations is both more complex and more elegant than early astronomers imagined. Rather than being a single, monolithic object, the Great Attractor is revealed to be a complex system of interconnected structures embedded in the cosmic web. At the heart of the Great Attractor region lies the Norma cluster, discovered through infrared and radio observations in the 1990s. The Norma cluster is a massive collection of hundreds of galaxies located about 220 million light-years from Earth. With a total mass equivalent to about 1,000 Milky Way galaxies, it represents one of the most massive galaxy clusters in our local universe. The Norma cluster is dominated by several giant elliptical galaxies, cosmic cities containing trillions of stars each. These galaxies formed through the merger of smaller galaxies over billions of years, growing into the massive structures we see today. The cluster is also filled with extremely hot gas at temperatures of tens of millions of degrees, detectable only through X-ray observations. But the Norma cluster is just one component of the Great Attractor complex. Nearby lies the Centaurus cluster, another massive collection of galaxies located about 170 million light-years away. The Centaurus cluster is actually closer to us than the Norma cluster and contains some of the brightest galaxies visible in infrared surveys of the zone of avoidance. Beyond these major clusters, the Great Attractor region contains dozens of smaller galaxy groups and clusters, each containing hundreds or thousands of individual galaxies. There's the Pavo cluster, the Triangulum Australe cluster, and numerous other collections of galaxies that were completely unknown before radio and infrared surveys revealed their existence. Radio observations have also revealed vast quantities of neutral hydrogen gas throughout the region, not just within individual galaxies, but also in the intergalactic medium between galaxies. This gas represents the raw material from which future generations of stars will form, and its distribution provides clues about how the Great Attractor region has evolved over cosmic time. But perhaps the most important component of the Great Attractor complex is also the most mysterious: dark matter. Based on gravitational studies, computer simulations, and observations of galaxy motions, astronomers estimate that dark matter outweighs all the visible matter in the Great Attractor region by a factor of about 6 to 1. This dark matter isn't uniformly distributed throughout space. Instead, it's concentrated into halos, roughly spherical concentrations that surround and encompass each galaxy cluster. These dark matter halos are invisible to all our telescopes, but their gravitational effects can be detected through gravitational lensing observations and through their influence on the hot gas in galaxy clusters. The dark matter halos in the Great Attractor region are among the most massive individual structures known in the universe. The largest ones contain the equivalent mass of thousands of Milky Way galaxies, concentrated into regions spanning millions of light-years. They represent the invisible scaffolding upon which the visible universe is built. Computer simulations show how these dark matter halos formed and evolved over billions of years. In the early universe, dark matter was distributed almost uniformly throughout space, with only tiny density variations. Over time, gravity amplified these variations, causing regions that were slightly denser to attract more matter and become denser still. As dark matter collapsed under its own gravity, it formed a hierarchical structure. Small halos formed first, then merged to create larger halos, which in turn merged to form even more massive structures. The Great Attractor region represents one of the endpoints of this process, a place where multiple massive halos have congregated and are still in the process of merging. The ongoing merger process explains many of the features that astronomers observe in the Great Attractor region today. The multiple galaxy clusters aren't randomly distributed. They're connected by filaments of galaxies and dark matter, and they show evidence of gravitational interactions with each other. Some clusters appear to be in the process of merging, creating substructure and disturbances in their galaxy populations and hot gas distributions. This dynamic picture of ongoing evolution is one of the most fascinating aspects of the Great Attractor. Unlike individual stars or planets, which can remain relatively stable for billions of years, massive cosmic structures like the Great Attractor are constantly evolving, growing through accretion of surrounding material and through mergers with other large structures. Observations with the Chandra X-ray Observatory have revealed direct evidence of these merger processes in action. X-ray images of galaxy clusters in the Great Attractor region show shock fronts, temperature variations, and other disturbances in the hot gas that fills the clusters, all signatures of ongoing gravitational interactions and mergers. These mergers release enormous amounts of energy. When two galaxy clusters collide, their hot gas atmospheres crash into each other at speeds of thousands of kilometers per second, heating the gas to even higher temperatures and accelerating particles to near the speed of light. The energy released in such collisions can exceed the total energy output of all the stars in both clusters combined. But perhaps the most remarkable aspect of modern Great Attractor research is how it has revealed the interconnected nature of cosmic structure on the largest scales. The Great Attractor isn't an isolated island of matter in an otherwise empty universe. Instead, it's connected to other massive structures by a network of galaxy filaments that span hundreds of millions of light-years. These filaments, composed primarily of dark matter with galaxies strung along them like beads on a string, represent the backbone of cosmic structure. They channel the flow of matter and energy across vast distances, connecting the Great Attractor to distant superclusters like Shapley and creating the large-scale flows that astronomers observe. The filamentary structure of the cosmic web emerged naturally from the gravitational collapse of matter in the early universe. Computer simulations show that as dark matter halos formed and grew, They tended to align along the directions of maximum density gradient, creating elongated structures that eventually became the filaments we observe today. Galaxies form preferentially within these filaments, where the density of matter is higher than in the voids between filaments. As galaxies move along the filaments under the influence of gravity, they eventually congregate at the nodes where multiple filaments intersect, creating the massive clusters and superclusters that dominate the observable universe. The Great Attractor sits at one of the most significant nodes in our local cosmic web. At least 3 major filaments converge in its direction, channeling galaxy flows from different parts of our cosmic neighborhood. This convergence explains why the Great Attractor's gravitational influence extends across such vast distances. It's not just the mass of the structure itself, but its position at a cosmic crossroads that makes it so influential. Understanding this cosmic web structure has profound implications for our understanding of galaxy evolution and star formation. Galaxies that live in the dense environments of clusters and filaments evolve differently from those in the sparse voids between filaments. They experience more gravitational interactions, more mergers, and more stripping of their gas content by the hot atmospheres of galaxy clusters. These environmental effects help explain why galaxy clusters like those in the Great Attractor region are dominated by massive elliptical galaxies rather than the spiral galaxies that are more common in less dense environments. The ellipticals formed through mergers of smaller galaxies and have had their star formation quenched by interactions with the hot cluster atmosphere. But the cosmic web also provides channels for the flow of pristine gas from the voids into galaxy-forming regions. This gas, which has remained relatively unprocessed since the early universe, provides the raw material for new generations of star formation. The balance between gas accretion along filaments and gas depletion in clusters is one of the key factors determining how galaxies evolve over cosmic time. Recent observations with radio telescopes have actually begun to detect the gas in these cosmic web filaments directly. Using techniques similar to those employed in studying the Great Attractor region, astronomers have mapped hydrogen gas along filaments connecting distant galaxy clusters. These observations provide direct confirmation that the cosmic web really does channel matter flows across the largest scales in the universe. The Great Attractor discovery has also contributed to our understanding of one of the most profound mysteries in modern cosmology: the nature of dark energy. Dark energy is the mysterious force that's causing the expansion of the universe to accelerate, and it represents about 70% of the total energy density of the cosmos. The gravitational effects of structures like the Great Attractor provide one of the few ways to study dark energy observationally. By measuring how the growth of cosmic structure has slowed over time due to the accelerating expansion, astronomers can constrain the properties of dark energy and test different theoretical models. Large-scale peculiar velocity surveys, including those that originally discovered the Great Attractor, are now being used to measure the growth rate of cosmic structure as a function of distance and cosmic time. These measurements provide crucial tests of our understanding of dark energy and gravity on cosmological scales. The results so far have been consistent with Einstein's theory of general relativity and with the simplest models of dark energy as a cosmological constant. But future surveys will provide much more precise measurements, potentially revealing deviations from these simple models that could revolutionize our understanding of fundamental physics. The Great Attractor has also played a role in testing one of the most fundamental assumptions of modern cosmology: that the universe looks the same in all directions on large scales. This assumption, known as the cosmological principle, is essential for interpreting most cosmological observations and for understanding the overall evolution of the universe. The discovery of massive structures like the Great Attractor initially seemed to challenge the cosmological principle. How could the universe be uniform on large scales if it contained such enormous concentrations of matter? However, As surveys have mapped larger and larger volumes of space, they've shown that structures like the Great Attractor are balanced by corresponding voids in other directions, maintaining overall statistical uniformity. Modern surveys now show that while the universe is highly structured on scales up to a few hundred million light-years, it becomes increasingly uniform on larger scales. The Great Attractor and similar structures represent fluctuations around the cosmic mean density, not violations of the cosmological principle. This hierarchical structure, with increasing uniformity on larger scales, is exactly what theoretical models predict based on the initial density fluctuations observed in the cosmic microwave background. The Great Attractor represents one of the largest individual fluctuations that can exist in a universe that's uniform on the largest observable scales. As we look toward the future, the Great Attractor will continue to play important roles in several areas of astronomical research. Next-generation surveys will map its structure in even greater detail, revealing the properties of individual galaxies within the complex and tracing the distribution of dark matter with unprecedented precision. The Euclid space mission, launched by the European Space Agency in 2023, will survey billions of galaxies across most of the observable universe, providing the most detailed map ever created of cosmic structure. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct complementary surveys focusing on the nearby universe where structures like the Great Attractor can be studied in detail. These future observations will address some of the remaining mysteries about the Great Attractor region. For example, while we know that the region contains multiple massive galaxy clusters, we don't yet have a complete census of all the galaxies and clusters present. Radio surveys are still discovering new structures hidden behind the zone of avoidance, and each discovery refines our understanding of the total mass and structure of the complex. Future observations will also trace the connections between the Great Attractor and the larger cosmic web in much greater detail. By mapping galaxy flows across larger volumes of space with higher precision, astronomers will be able to understand exactly how matter flows through the cosmic web and how structures like the Great Attractor grow and evolve over time. There's also the tantalizing possibility of discovering new types of objects or phenomena in the Great Attractor region. The dense environment and complex dynamics of the region make it a natural laboratory for studying extreme astrophysical processes. Future observations might reveal new types of galaxy interactions, unusual dark matter distributions, or even exotic objects like intermediate mass black holes. Advanced computer simulations will continue to play a crucial role in Great Attractor research. Next-generation cosmological simulations will model the formation and evolution of the region in much greater detail, potentially revealing subtle effects that current observations have missed. These simulations will also help astronomers understand how the Great Attractor fits into the broader context of cosmic structure formation. By simulating the evolution of large volumes of the universe, researchers can study how many Great Attractor-like structures should exist, where they should be located, and how they should evolve over cosmic time. But perhaps the most exciting prospects for Great Attractor research lie in the potential for entirely new types of observations. Gravitational wave astronomy, which has already revolutionized our understanding of black holes and neutron stars, might eventually be able to detect signals from the Great Attractor region. The dense environment of galaxy clusters makes them likely sites for black hole mergers and other gravitational wave sources. Future gravitational wave detectors, both ground-based and space-based, might be sensitive enough to detect these signals and use them to study the internal dynamics of structures like the Great Attractor. Similarly, advances in neutrino astronomy might provide new ways to study the Great Attractor. Neutrinos are produced in various high-energy astrophysical processes and can travel through the universe essentially unimpeded. Detecting neutrinos from the Great Attractor region could provide information about processes that are invisible to conventional telescopes. There's even the possibility that dark matter itself might eventually be detected directly through its particle interactions. If dark matter particles interact with ordinary matter in ways that can be detected in laboratory experiments or space-based detectors, then regions of high dark matter density like the Great Attractor might produce detectable signals. The search for dark matter particles is one of the most active areas in modern physics, with experiments around the world looking for evidence of these elusive particles. A positive detection would revolutionize our understanding of the Great Attractor and similar structures, revealing the microscopic nature of the invisible scaffolding that supports the visible universe. As we contemplate these future possibilities, it's worth reflecting on how the Great Attractor discovery has changed our understanding of our place in the universe. When the Seven Samurai first announced their discovery in 1986, the Milky Way seemed like a relatively isolated galaxy in a mostly empty universe, occasionally interacting with nearby neighbors like Andromeda but otherwise independent. Today, we know that our galaxy is part of an intricate cosmic ecosystem, connected by invisible threads of gravity to structures hundreds of millions of light-years away. The Great Attractor isn't just pulling our galaxy through space. It's orchestrating a cosmic dance that involves thousands of galaxies across vast distances. This realization has profound implications for how we think about our cosmic future. Our galaxy's ultimate destiny is tied to the evolution of the Great Attractor and the larger cosmic web of which it's a part. As the universe continues to expand and evolve, our motion through space will be determined by the gravitational tug-of-war between these massive structures. In the near term, meaning the next few billion years, our galaxy will continue its journey toward the Great Attractor region. But we'll never actually reach it, because the expansion of space will eventually overcome the gravitational attraction, causing the Great Attractor to recede from us faster than we can approach it. This cosmic recession will begin gradually but will accelerate as dark energy becomes more dominant in determining the universe's evolution. Eventually, all the galaxies currently flowing toward the Great Attractor will reverse direction and begin moving away from it, as the expansion of space overwhelms even the strongest gravitational attractions. In about 100 billion years, the cosmic web that currently connects galaxies across hundreds of millions of light-years will dissolve. Laniakea will break apart, and the Great Attractor will become isolated from its current sphere of influence. The cosmic flows that we observe today will become just a memory preserved in the motions of stars within individual galaxies. But that's still far in the future. For now, we live in a remarkable epoch when gravity still dominates over cosmic expansion on large scales, allowing structures like the Great Attractor to exist and influence the motions of galaxies across vast distances. This perspective of living in a specific moment in cosmic history when certain phenomena are possible is one of the most profound insights that the Great Attractor has given us. The universe is not static and unchanging. It has a history, a present, and a future, and the phenomena we observe today are specific to this particular epoch. The Great Attractor represents the universe during its mature phase, old enough for gravity to have assembled massive structures from the initial density fluctuations left over from the Big Bang, but young enough that these structures can still grow through gravitational attraction. It's a window into the architecture of the cosmos during its most structurally complex phase. In many ways, the story of the Great Attractor is also the story of human curiosity and ingenuity. Faced with evidence of something massive and influential but completely invisible, astronomers didn't give up or dismiss the observations as errors. Instead, they developed new technologies, new techniques, and new ways of thinking about the universe. They learned to see with radio waves and infrared light, to map invisible matter through its gravitational effects, and to use computer simulations to understand phenomena that could never be observed directly. They turned the entire electromagnetic spectrum into a toolkit for cosmic archaeology, and they used the laws of physics as a guide to understanding structures that defied direct observation. The Great Attractor discovery represents one of astronomy's greatest detective stories, a mystery that was solved through decades of patient observation, technological innovation, and scientific collaboration. It shows what humanity can accomplish when faced with seemingly impossible challenges. The story also illustrates the interconnected nature of scientific progress. The Great Attractor couldn't have been discovered without Vera Rubin's work on dark matter, Edwin Hubble's discovery of cosmic expansion, Einstein's theory of general relativity, and countless other scientific advances. Each breakthrough built on previous discoveries, creating a cumulative understanding that no individual scientist could have achieved alone. Today, the Great Attractor continues to be a source of new discoveries and insights. Each new observation reveals additional details about its structure and evolution. Each improved computer simulation provides new theoretical insights into how such massive structures form and evolve. Each technological advance opens new windows for studying its properties. But perhaps the most important legacy of the Great Attractor is the perspective it has given us on our place in the cosmos. We are not isolated observers in an empty universe. We are participants in a vast cosmic community, connected by invisible bonds of gravity to structures that span unimaginable distances. Every atom in your body was once part of this cosmic flow. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the nuclear furnaces of stars that were themselves part of galaxies flowing through the cosmic web toward massive attractors like the one we've been discussing. You are literally made of star stuff that has been on an epic journey through space and time, shaped by forces that operate across hundreds of millions of light years. The Great Attractor isn't just something distant and abstract. It's part of your cosmic heritage, part of the story of how you came to exist. This cosmic perspective can be both humbling and inspiring. Humbling because it reminds us of how small we are in the vast scheme of things. Inspiring because it shows us that we are part of something much larger and more magnificent than our everyday experience suggests. The Great Attractor also serves as a reminder that the universe is far stranger and more wonderful than we often imagine. Who could have guessed that invisible rivers of dark matter channel the flow of galaxies across hundreds of millions of light years? Who could have predicted that our own galaxy is caught up in gravitational currents that connect us to some of the most massive structures in the known universe? These discoveries remind us to approach the universe with both scientific rigor and a sense of wonder. The cosmos has a way of surprising us, of revealing phenomena that challenge our assumptions and expand our understanding. The Great Attractor was one such surprise, and there are undoubtedly many more waiting to be discovered. As we conclude this journey through the mystery of the Great Attractor, it's worth considering what this story tells us about the future of astronomical discovery. The Great Attractor was found not through a single brilliant insight, but through the gradual accumulation of observations, measurements, and theoretical understanding over many decades. This suggests that the next great cosmic discoveries will likely emerge in similar ways through patient observation, technological innovation, and the gradual assembly of evidence that reveals new aspects of the universe's architecture. The cosmos still holds many secrets, and unlocking them will require the same combination of scientific rigor, technological creativity, and intellectual curiosity that led to the Great Attractor's discovery. The story also reminds us that the universe operates on scales that challenge human intuition. The Great Attractor influences our motion through forces that operate across distances so vast that light from its far edges began its journey to us when the first complex life was emerging on Earth. Yet these same forces are delicate enough that they can be detected through careful measurements of galaxy velocities and subtle variations in the cosmic microwave background. This combination of vast scale and subtle effect is characteristic of many of the most important phenomena in modern astronomy. It requires both powerful instruments and sophisticated analysis techniques to detect and understand these cosmic influences. The Great Attractor discovery exemplifies how modern astronomy has become a collaborative effort involving thousands of scientists working with some of humanity's most advanced technologies. Looking ahead, the Great Attractor will continue to be an important laboratory for testing our understanding of cosmic structure, dark matter, and the fundamental forces that shape the universe. As our observational capabilities continue to improve and our theoretical models become more sophisticated, we can expect new insights into its nature and significance. But beyond its scientific importance, the Great Attractor serves as a powerful symbol of humanity's ability to uncover the hidden workings of the cosmos. It represents our refusal to accept "we can't see it" as a final answer, and our determination to find creative ways around seemingly impossible observational challenges. The Great Attractor reminds us that we live in a universe full of wonders, a cosmos where invisible rivers of matter flow across hundreds of millions of light years, where the motion of our own galaxy is determined by gravitational influences that reach across vast distances, and where patient scientific investigation can reveal the hidden architecture that connects all things. As you go about your daily life, remember that you are part of this cosmic story. You are traveling through space at over 2 million kilometers per hour as part of a gravitational flow that connects you to some of the most massive and distant structures in the observable universe. The Great Attractor is calling, and you are answering, carrying forward the cosmic heritage that connects all matter and energy in the universe. This is the legacy of the Great Attractor, not just a scientific discovery, but a revelation about our place in the cosmic community. We are not alone in the universe, not isolated on our small planet in our small solar system. We are part of something magnificent and vast, participants in a cosmic dance that has been unfolding for billions of years and will continue for billions more. The universe is calling, and we are all traveling together toward destinations we can barely imagine, guided by forces we are only beginning to understand. The Great Attractor is just one waypoint on this incredible journey, a journey that encompasses not just our galaxy, but our understanding of what it means to be part of the cosmos itself.